In chapter 3, we have learned about the fundamental metric tensor, associated vectors, angle between two non-null vectors, etc. Now, here in chapter 4, we shall learn about the partial derivatives of the fundamental metric tensor. In 1869, B. Christoffel has framed a linear combination of the partial derivatives of Gij and named as Christoffel symbols. So, in chapter 4, module 1, we shall learn about the Christoffel symbols and their properties and the transformation rule for these Christoffel symbols, and we will show that these Christoffel symbols are not tensor quantity. Now, in chapter 4, module 1, we shall learn about Christoffel symbols and their properties and the transformation of Christoffel symbols from one coordinate system to another coordinate system. In the year 1869, B. Christoffel has introduced two types of combination of partial derivatives of fundamental metric tensors known as Christoffel symbols. He has constructed a function denoted by third bracket ij comma k. He has introduced this one as a first kind of Christoffel symbol, which is equal to half del g I k by del x j plus del g j k by del x I minus del g I j del x k, where I j k is running from 1 to 3 to n. So, this linear combination of the partial derivatives of the fundamental metric tensor is known as Christoffel symbol of first kind. Another set of functions defined by gamma k I j, which is equal to the product of g k alpha third bracket I j alpha, is known as Christoffel symbol of second kind, where g k alpha is the contravariant fundamental tensor. Now, as g k beta g k alpha is equal to del alpha beta, we can get g k beta gamma k I j is equal to del alpha beta I j alpha, and that is equal to third bracket I j beta, which is the Christoffel symbol of first kind. So, this is the relation between the Christoffel symbol of first kind and second kind. The number of independent components of Gij is half n into n plus 1 for a Riemannian space of dimension n. We can easily prove this one, and the number of independent Christoffel symbols will be half n square into n plus 1. In Euclidean space, for rectangular Cartesian coordinate system, Christoffel symbols are all 0, because all Gij's are equal to 1 for I equal to j, and Gij's equals to 0 for I not equal to j. So, their partial derivatives are all 0. Therefore, the Christoffel symbols are all 0. Now, let us see the properties of Christoffel symbols. First one is for the Christoffel symbol of first kind, that is third bracket I j k equals to third bracket j I k. So, it is symmetric with respect to the I j index. Similarly, for the Christoffel symbol of second kind, gamma k I j is equal to gamma k j I. We can easily prove these properties. Third one is del g I j by del x k equals to Christoffel symbol of I k comma j plus j k comma I. The fourth one is again the relation between the Christoffel symbol of first kind and the Christoffel symbol of second kind, and we can prove it also easily. G L M gamma L I j, and gamma L I j can be written as G L k Christoffel symbol I j comma k, and G L M G L k can be written as del k m. So, the expression takes the form Christoffel symbol of first kind as I j comma m. For the 5, gamma m I l equals to G m j third bracket I l comma j, we can prove it in the following way: gamma m I l equals to G m alpha, Christoffel symbol of first kind I l comma alpha, and that can be written as G m j, Christoffel symbol of first kind I l comma j, because alpha is a dummy index here. So, we can replace alpha by j. Now, the sixth property is an important property, that is del g m k by del x l is equal to minus g j m gamma k j l minus g I k gamma m I l. Proof follows in the following way: we know that g I j g I k is del k j. Now, partial differentiating with respect to x to the power l to the above expression, we get g I j del g upper I k by del x l plus g upper I k del g I j del x l equal to 0. Now, inner multiplication by g j m gives g I j g j m del g upper I k by del x l plus g upper I k g upper j m del g I j del x l equal to 0, which gives del m I del g upper I k by del x l plus g j m g I k del g I j del x l. So, after this step, with the help of del m I del g I k del x l, we get del g m k del x l plus g upper j m g upper I k del g I j del x l equal to 0. So, we can write del g m k del x l equals to minus G upper j m G upper I k del G I j del x l. Now, from property 3 of Christoffel symbols, we can write the expression of del G I j by del x l, and the above relation takes the form del G m k del x l equals to minus G j m G I k. In the bracket we are getting this Christoffel symbol of first kind I L j plus j l I. So, by multiplication in the right hand side we get this expression, and from this relation we are getting minus G I k gamma m I l minus G j m gamma k j l. So, this is the property 4, that we are getting del G upper m k by del x l equals to minus G j m gamma k j l minus G I k gamma m I l. Example 4.1 is also a property where we can see that gamma I j becomes del x j of log root g, where g is the determinant of g I j, and provided g is not equal to 0. The proof follows like this: g upper I k equals to cofactor of g I k in g by g, where g is the determinant of g I j not equal to 0. It is defined earlier. So, cofactor of g I k in g can be taken as g upper I k, capital G upper I k by g, where g I k's are the cofactors of g I k in g. Now, derivative of a determinants is obtained by differentiating each row of its separately and keeping the other rows same and summing the resulting determinants thus obtained. So, del G del x j will give G upper I k, that is capital G upper I k, into del G upper I k by del x j. And now, G I k can be expressed as G into G I k del G I k del x j. Now, again using the property of Christoffel symbol, we get G G I k Christoffel symbol I j k comma k plus Christoffel symbol k j comma I. And just breaking the bracket, we are getting the expression. Now, in second term, replacing dummy index k by I and I by k, we get this one G G I k I j k plus G G k I j k, which gives the twice of this, twice G G I k I j k, since G k I equals to G I k, because G is a symmetric contravariant tensor of rank 2, and G G I k I j k can be expressed as gamma I j. So, we have gamma I j equals to del x j log root g. Now, let us calculate the Christoffel symbols of second kind in cylindrical coordinate system. In cylindrical coordinate system, we know from the previous chapters that ds square have the expression dx1 square plus x1 square dx2 square plus dx3 square, where g11 equals to 1, g22 equals to x1 square and g33 equal to 1. So, the determinant of gij, that is g, is coming to x1 square and which is not equal to 0 unless x1 equal to 0. Now, Christoffel symbol of first kind 2 2 comma 1 is equal to minus x1 and 2 1 comma 2 is equal to x1. So, only these two Christoffel symbols of first kind exist for the cylindrical coordinate system. So, from the definition of Christoffel symbol of second kind, we get gamma 1 2 2 equals to minus x1 and gamma 2 1 2, that is equal to gamma 2 2 1 by the property of Christoffel symbol. They are equal and this is coming to 1 by x1. We can easily calculate this Christoffel symbol of second kind by the help of Christoffel symbol of first kind. So, in section 1 of module 1 of chapter 4, we have learned about the Christoffel symbols and their properties. Also, we have seen that how the Christoffel symbols can be calculated in cylindrical coordinate system or in any coordinate system. Now, we shall see in the second section the transformation rules for these Christoffel symbols, that is Christoffel symbols of first kind and Christoffel symbols of second kind. And here we will see that Christoffel symbols are not tensor quantities. So, they are only noted as symbols. Now, in this section we see that how the Christoffel symbols change if the coordinate system change from xi to x bar I. From the law of transformation of covariant tensor of type 02, we see that g bar Lm equals to g I j del xi del xj del x bar L del x bar n. This is the transformation rule for the covariant tensor of type 02. Now, differentiating this expression with respect to x bar m, that means partial derivative, we are doing the partial derivative, we find del g bar ln by del x bar m equals to del g I j del x k del x k del x bar m, because g I j's are the functions of x I. So, we can't find the derivative with respect to x bar m. So, we are doing del g I j del x k del x k del x bar m and then del x I del x bar L del x bar j del x bar n plus g I j del 2 x I del x bar m del x bar L del x j del x bar n plus g I j del x I del x bar L del 2 x j del x bar m del x bar n. Similarly, we find the other partial derivatives like this. These two are the partial derivatives of g bar m n with respect to x bar L and g bar L m with respect to x bar n. Now, from the definition of christoffel symbol of first kind, Lm comma n bar, that is, it is in x bar I coordinate system, is equal to half del g bar ln by del x bar m plus del g bar mn by del x bar l minus del g bar lm by del x bar n. And if we put the above expressions obtained earlier and after some calculations, we get this expression, that is christoffel symbol Lm comma n bar equals to christoffel symbol Ik comma j del xi del x bar l del xj del x bar n del xk del x bar m plus gij del 2 xi del x bar l del x bar m del xj del x n. So, from this transformation rule, what we can observe that for the second term there is a term which is del 2 xi del x bar l del x bar m, and for the second term this transformation rule does not give any transformation for tensors. So, inner multiplication both sides by g bar ns, the corresponding equation will give, after some calculations, christoffel symbol of Lm comma n bar g bar ns equal to I k comma j g j q del xi del xk del x bar s, and here del x bar l del x bar m del x q plus g I j g j q del 2 xi by del x bar l del x bar m del x bar s del x q, where g bar ns equals to g p q del x bar n del x bar s by del x p del x q. So, these are the transformation rules for the contravariant fundamental metric tensor. So, from the above expression we are getting gamma bar S Lm equals to gamma q I k del xi by del x bar l del xk by del x bar m del x bar s by del x q plus del 2 xi del x bar l del x bar m del x bar s by del x q. So, this is the transformation rule for christoffel symbol of second kind, and it is also not a tensor due to presence of the second term. Now, inner multiplication with del x r del x bar s from both sides, we get del 2 x r by del x bar l del x bar m equals to gamma bar S Lm del x r del x bar s minus gamma r I k del x I del x k del x bar l del x bar m. So, the above expression for the christoffel symbol of second kind, we get gamma bar S Lm equals to g p q del x bar n del x p del x bar s del x q I j comma k del x I del x bar l del x j del x bar m del x k del x bar n plus g p q del x bar n del x p del x bar s del x q, g I j del x I by del x bar n del 2 x j del x bar s del x bar m. By inner multiplication with del x r del x bar s, we obtain del x r del x bar s gamma bar s L m equals to gamma p I j del x bar s del x p del x I del x bar L del x bar j del x bar m del x r del x bar s plus del x bar s by del x j del 2 x j del x bar L del x bar m del x r by del x bar s. Taking j equal to r, we get the expression for the double derivative of x j, that is del 2 x j by del x bar L del x bar m equals to del x r by del x bar s gamma bar s L m minus gamma r I j del x I by del x bar L del x j by del x bar m. Now, this expression will be used to define covariant differentiation, which we shall discuss in the next module. So, in section 2 of module 1 of chapter 4, we have learned about the transformation rules of Christoffel symbols of first kind and second kind. Here we have seen that Christoffel symbols are not tensor quantities, as they do not follow the transformation rules of tensor quantities. Here we have also obtained a second order partial derivative of xi's, which we shall use in the next module to define the covariant differentiation of tensors. With this, we finish this module of chapter 4, module number 1.